Hello, thank you for joining us today for the third and final webinar in our data science series, Curating Data and Integrating the Wolfram Data Framework. I'm very pleased to welcome today's presenters, Alan Joyce, Director of Content Development with Wolfram Alpha, and Aaron Enright, Data Scientist with Wolfram Alpha. Alan will begin today's webinar with his presentation on how to augment your work with the Wolfram knowledge base. Aaron will follow with his talk, Creating a Data Resource, where he'll import data from the American Presidency Project Online Data Archive and show us how to clean, structure, and visualize the extracted data. We'll also be sharing some online resources and links with you along the way to guide you as you become more familiar with the Wolfram Data Framework. And Alan and Aaron will take time to respond to your questions at the end of the webinar. My name is Jamie Peterson, Technical Programs Manager with Wolfram Research, and I'm your online host for this data science webinar series. I'm joined by several of my Wolfram colleagues behind the scenes to respond to your typed questions during the webinar and help point you to the resources you need. Today's webinar is an opportunity for you to get started using the Wolfram language for algorithmic knowledge and extracting data with the Wolfram Data Framework. The presentation notebooks will be available to you to download during the webinar. And before passing the microphone to Alan, I'm going to ask a quick poll question. It's going to ask about the Wolfram technologies you've used. When the poll question appears on your screen, please select your responses and we'll share the answers after everyone has a chance to respond. As you can see, looks like a good majority, 78%, have used Mathematica and the Wolfram language, and we're grateful for that. But about half of you have also been working with Wolfram Alpha, and 30% the Wolfram Cloud. The Wolfram Data Repository will be something we'll talk more about today, so you will learn more about that. So thank you for giving us those results. And Alan, I think I found those interesting. I'm ready to turn things over to you following that poll.
Great, thanks very much, Jamie. Hopefully you can see my screen now. So I'm Alan Joyce. I'm the Director of Content Development for Wolfram Alpha, and today I'll be sharing a little bit of history and an overview of some of the key features of the Wolfram Data Framework, as well as some tips and examples of how you can effectively use this framework to improve and extend external data sources you may be working with your own projects. So what is the Wolfram Data Framework? At its core, it's a collection of Wolfram language symbols that represent real-world objects, concepts, and data, the data structures that contain and organize the data represented by those objects, and functions that can operate on, analyze, visualize that data. So at the core of all this is the Wolfram knowledge base, which contains millions of canonical entities from hundreds of different domains representing all different kinds of objects, people, countries, chemicals, elements, books, movies, anatomical structures, even Pokemon. Each of those entities can have dozens or even hundreds of distinct properties whose values are encoded in flexible, powerful Wolfram language representations of things like quantities and units, dates and times, geodetic datum, graphs, and more. So the development of this framework has been proceeding steadily for more than a decade now. From the launch of the first built-in data packlets in Mathematica in 2007, through the launch of Wolfram Alpha, which is itself mostly a giant Wolfram language program, and then the subsequent integration of that Wolfram Alpha knowledge base back into the language, and then the introduction in the language of more features like data objects, time series, and more, and most recently the launch of the Wolfram Data Repository just last year. So longtime users of the Wolfram language, it seems like we've got a fair number of them today, will most likely have some familiarity with the earliest data packlets. Country data, element data, chemical data, these were all domain-specific functions that give direct access to data on entities of different types. Quantities, units, numbers, time series, 3D graphics, models of molecules, all sorts of useful data in a relatively small number of domains, though. After that, then we introduced Wolfram Alpha, and this started from the backbone of those very early data packlets, but added hundreds of other domains as well as a simple, non-programming interface. Wolfram Alpha was designed to allow users to access all that data, retrieve it, perform sophisticated computations with data from all those domains using just natural language queries. what Wolfram Alpha didn't do, at least at the time, was let you delve deeper into the data and extract raw data, use it in your own projects. So the next step was really integration, a very early integration of Wolfram Alpha itself into the Wolfram language. So the Wolfram Alpha function essentially gives you a view of Wolfram Alpha results inside a notebook. Wolfram Alpha and any input will return a result in a list of pods. It's also allows for the extraction of other kinds of data from those pods. So you might want to get computable data, time series data. Let me just refresh here a moment. But what this allows other people, and we've seen people use a lot of really interesting things here, it lets you pull some of that data from Wolfram Alpha and use it directly like you would any other data packlet data, things from country data, element data, anything else. And this is really useful, but still, Wolfram Alpha is essentially designed as a one-shot experience. You've got a single question and an answer to that. There isn't really a good way to do lots of programmatic diving into these domains. So where this really became a framework that's of real use to Wolfram language users was with the full exposure of entity value and the entity framework. So this framework really is essentially the same framework used internally by Wolfram Alpha to represent and compute answers to questions that come through the Alpha website or our API. A control equals opens up a natural language input field that can interpret entities on their own. It can interpret entities and their properties and retrieve the values for those entity property combinations. They can be more complex queries, like you can type in, give me the 5 largest countries by population. And that gives you an implicit entity class that you can then list out the members of that class and get access to those entities and then any of the other data you want to retrieve for those. And this is kind of the way that we view data inside of Alpha. And now this is exposed in the Wolfram language, and so people have access to all the sorts of birthplaces, dates, quantities, everything that you might want to know about people and countries and places and platypuses, or is it platypi? But so this has been the culmination of a long process of learning how to work with data in the Wolfram language, expanding on those data sets in Wolfram Alpha, and then bringing all that knowledge back to the Wolfram language so that users can make use of what's in the knowledge base, can make use of all these structures, and work a lot better with data of their own and enhance it with stuff that's in the knowledge base. I'll touch briefly here on the Wolfram Data Repository, which is the most recent addition here. Because the task of growing the Alpha knowledge base is essentially never ending. There's more data being added all the time in every possible domain, and there's a world of data out there that may be too niche or specialized to be of general interest to Wolfram Alpha users. It's going to be a long time before we get to all of those sorts of data sets, but the data repository is a chance to have, it's a public repository. There are some Wolfram curated data sets in there. Wolfram language users can submit data sets to it and share them with other people. The resources are searchable directly within the language and immediately accessible. And this is really the key point, and what's relevant to our talk today is these are data sets that have gone through a process of curation and enhancement and applying Wolfram data framework structures and entities to these raw data sets so that they're instantly useful in the Wolfram language. You can make use of all the sorts of advanced visualization, time series operations, retrieving additional data on canonical entities without having to go through the process of cleaning those up yourself. And this is the kind of thing where the raw data set here is just a big CSV. This is a nicely formed data set that has quantities, it has data objects, it has coordinates. You can immediately generate maps with a single line of code and do all sorts of advanced operations on it. I'm going to mention this here. Stephen introduced this data curation hierarchy when we launched the data repository. It's a useful way of thinking about the overall process of bringing data into the language and the different levels of cleanup and curation and enhancement you can apply to them. I think for today, between Aaron and I, we're touching mostly on steps 4 through 7. The 0th through the 3rd step are mostly different levels of quality and structure that have been applied to raw data sets. Once we get in here, we're talking about normalizing things to quantities, dates, locations, entities, creating custom entity stores, doing some analysis of that data. So this is sort of the zone that we're focused on today. So a relatively simple example here. I'm starting with some sample data from the U.S. Department of Health and Human Services, and this is a data set of Head Start Center locations. For people who work with the Wolfram language, you know that just getting in something that's a nice clean CSV is as simple as import the file location or the web address here. Once you've got that, though, this is a little hard to make sense of in some ways. It's pretty clean. It's a simple data set. You've got a header row. You've got some data. You can see there are coordinates. You can see there are states and cities. There are things we might align here. But if you want to work with this, I find that it's a little bit easier to start putting things into associations. So here I'm building a list of associations by threading the header row across all the rest of the rows in this data set. And I end up with a bunch of records that are like this. So every field has a name, and that means you can go in and you can start just picking out specific columns out of that data set. If I just want to get the name, city, and state for all these things, that's a trivial thing to do. Personally, and for the purposes of the data repository and as people are sharing data sets, I find that it's nice to go a step further and actually put things into a Wolfram language data set. This preserves most of the functional features of associations, but you get a nice interactive interface. You can page through the data. You can dig down into individual columns if you want to and look at values. But it's a nice way of starting to work with larger structured data sets. And the same thing here. You can start selecting out bits of that data set. You can say, I just want to get all the rows that are early Head Start centers in Rhode Island, and it's a matter of one line of code to pull all that stuff out. So we've got this in a nice Wolfram language structured form. At that point, we want to start about looking at normalizing some of these values. We want to apply some of the really useful features of the Wolfram data framework to this data set. So we could see that before there were coordinates. There's a latitude column and a longitude column. This is one of the easiest things to clean up and normalize here, so we can start with that. And here I'm just, you could go through and start replacing the existing content. I'm just prepending a column so you can see how things look in the raw data set compared with what I'm adding here. So I'm prepending a column that I'm just going to call position, and I'm grabbing the latitude and longitude values, wrapping those in geoposition, and mapping that over the whole data set. And I end up with a column for each center that has a geoposition for each of those locations. And so once you've got that, then immediately, geohistograms, list plots, all the sorts of geographic visualization that you can do in the language, you can do very easily. You can start to get a sense of, where's the greatest density of some of these locations. Maybe unsurprisingly, it's major population centers, but still, it's an easy thing to do. And you could dig down into specific states, other locations, and look at how these centers are distributed there. This data set doesn't really have any fields with quantitative values, things that have units, but the same kind of process applies. We could take that earlier example I was showing from the data repository of a meteorite data set. And this is just a NASA data set. It's a JSON file. We can import this, make it into an association, wrap that in data set, and we've got, this is the raw data. So we can see again here, there are coordinates that we would want to clean up. There's also a mass value. And we can find out from looking at the data source that mass column is values in grams. So you can start thinking, well, it would be really useful to have those not just as numbers, where if I share this data set with someone, I have to say, okay, well, mass is in grams, the years or dates, another column is in meters. But we turn these things into Wolfram language quantities. So the trivial thing, at least as it would seem, is, again, let's add a column here, and let's call it mass quantity. And I'm just going to take all the mass values, and I'm going to wrap them in quantity and say those are grams, and map that over all the rows that have a mass. Great, I've got grams. Unfortunately, you might say, okay, now I want to start visualizing those things. The bar chart fails because it turns out the original import, those values were strings. And all we did was say, take that value, stick it in quantity. Quantity doesn't know that one string is supposed to be larger than the other, so you need to think a little bit about what state the raw data is in. You could have gotten around that by converting those values to integers or reals at that stage. But what is even more useful in many cases is learning how to use interpreter in the Wolfram language. And interpreter, there are as many interpreters, actually more, as there are different types of entities in the Wolfram language. So there's an interpreter for buildings, for countries. There are also other kinds of computed and structured interpreters for quantities, dates and times, all sorts of different entities and other types of structures. So in this case, we could say, again, let's just take all the rows that have a mass value, and we are going to interpret each of those mass values as being a quantity with the unit grams. And so what we get out there, again, looks like the same column, but this actually does what we want it to. So we can start visualizing things. We can generate plots of those values. We can start sorting and extracting data. Here I'm taking the top 5 meteorites by mass and grabbing their names and masses. And if you're like me and you still haven't quite gotten completely internalized the metric system, and it's hard to think about what 23 million grams is, having things as quantities means you can just instantly convert those to any other compatible unit that you might want to. So one of the things that's really, really powerful and flexible about having things represented as canonical data types, quantities, dates, and so on. So coordinates, quantities, these are immediately useful. You can compute with them right away. They have all sorts of additional features. It lets you use all sorts of other functions in the language. But when you have columns in a data set where some of those values can be aligned to any of the canonical entities in the Wolfram language, that opens up a whole other world of computation here. That means that you align some data value like Alabama or gold or Mount Everest to the canonical representation of that thing in the language, and then you can access any of the curated data values that we have for those specific entities. Data values that may not be in some related data set that you're working with, but can be used to enhance that data set. So since this data set has a column with US state abbreviations, that's pretty easy to align. And here we're just going to say there is a US state interpreter, and I'm going to apply that to the state column in this data set, which has state abbreviations, and just add a column for that. And so we end up with states. This is an alignment that generally I'm going to be pretty confident in, as long as we believe that all the abbreviations in that column are state abbreviations. We're going to get them right the first time. There's no redundancy in those abbreviations. So if you believe all of them to be US states, that's what you're going to get out here. So you might be feeling really proud of yourself and say, well, I'll do the same thing with the city field. But when you do that, where you're just saying, I want to interpret whatever's in the city column as a city, the city column only has a city name. It doesn't have any other context to it. It doesn't say that it's, for example, Alton, Missouri. So interpreter works basically like Wolfram Alpha. You feed in a string, and we try to interpret it as a particular thing. By default, that may not be the specific thing that's referred to in your data set. For whatever reason. This may be because I'm currently in Illinois, so it thinks that I'm most interested in the Alton that's closest to me. This is the Alton, Illinois, the Alton city that I get out. For things like Brooklyn, Ohio. This was Brooklyn, New York. which there's an extra complication. You know, Brooklyn, New York is not really a city, it's a borough, it's a county. And so it's an administrative division type entity in the Wolfram language. So there's a few tweaks that we need to make here. But you can work around this, again, pretty easily by saying, I'm going to take this time, I'm going to join together the city and state columns. So instead of just Alton, I'm going to have Alton, Missouri. And I'm going to interpret that string as a city or an administrative division. And I'm going to add that again as the city column here. And so what we get out here, you know, the states match up, things look pretty good. This seems like a pretty plausibly good alignment between all of these cities and states. There's a lot of power here, but there also, because there is so much data and because there can be ambiguity when you're trying to interpret any particular string, the more context you can feed to interpreter, often the better your results are going to be. So it's just something to watch for when you're doing this. So I'm gonna shift here, and instead of continuing with the raw data set I'm working with, there is an expanded version of this data set in the Wolfram data repository already that already has cities and states and zip codes and other things aligned to their canonical representation in the language. So just to switch to this, and as a demonstration, in this data set, we have, for example, zip code entity alignment for each of these centers. So because we have that, we could also start inserting data from the Wolfram knowledge base into this external data set. So for this example, we're saying, let's take the zip code entity associated with each center, and I'm going to add a column with the population under 5 for that zip code and the median income. And this is just taking that entity and accessing the property population with a qualifier where age goes to an interval of quantity 0 to 5 years. And household income, again, just taking that entity and accessing the property for median household income and mapping that over here, just a sample of rows. And what you get out is some really potentially useful data for the zip code associated with each one of these centers. So then we can start putting all this together. Here's, let's do this for a specific subset here. I'm going to take all of the Head Start locations that are in the city of Pittsburgh. I'm going to do the same operation. I'm going to prepend columns with population under 5 and median income for each of those zip codes. And then I can generate a geo-region value plot, basically a choropleth map, heat map for each of those properties. And then just a list plot of all of the centers that were pulled out in this subset of the data. And then with that, you can start taking a closer look at, you can look where the distribution of centers is and how that matches up with different regions. The first here we have population under 5 by zip code. You can see darker areas are larger populations. Down here, median household income, darker areas are higher household income. And this is the start of some analysis of where these centers are located in relation to centers of relevant population and in relation to where most of the household income is concentrated in this area. So you can see that having that alignment is not just a convenience. I mean, it is something that lets you tap into a much larger data set of curated knowledge that you can add to your own data sets. The last thing I'm going to touch on here, so I leave plenty of time for Aaron and for questions, is custom entities and entity store. I mean, obviously there are many more entities in the known universe than we have got in Wolfram Alpha right now or in the Wolfram knowledge base. And so entity store is a very powerful tool. And this is, again, coming right out of how we describe and define data types in Wolfram Alpha. And this lets you define your own entity types, which can be used just like any of the built-in types in the language, can be deployed and shared with other people who are using the Wolfram language so that they can pull in that data and use these entities in combination with the things that are built in. Building a really nice entity store that has nice labels on all the entities and properties is not a completely trivial task. It just takes some time and tweaking, but you can get something in perfectly usable shape with very little time. So just as an example here, the data set we're working with for Head Start locations, there isn't a unique identifier for each of these centers in the data set. So I'm constructing something that I assume is going to be unique. I'm joining together a grant number, a center name, and the zip code name for each of these things. And they end up looking like they're unique values, creating an association between those identifiers and all the data for each of these centers. And if you've got something that looks like this, association where the keys are the identifiers for a thing, and then the value of that outer association is a bunch of other key value pairs with essentially properties and property values. Creating an entity type is as simple as saying entity store, name of the entity type, entities goes to this data set up here. And so you register that as an entity, and then you can start using this just like any other entity type in language, countries or cities or anything else. Get a list of the entity properties for Head Start locations. I can create an implicit entity class that lets me look up Head Start locations where the city of the center is Cleveland and get a list of those. Start generating plots, take that list of centers and do a geo list plot of them based on all their coordinates. So entity store could be a whole talk unto itself to get into all the details of curating and constructing a nice custom entity store. But in general, it's a really nice way of extending what you've got. When you've got a really good data set that you want to work with the same way you use built-in entities in a language, entity store is a great tool. I don't think that I have anything else I need to cover right now. I want to make sure I leave time for questions on this part of the presentation, and Aaron has time to go a little bit deeper into the process of curating messier data sets and more complicated data curation processes. So I can stop there and we can take questions. Are you planning to restore the full functionality of the financial data function? Your question from Tobias. Great question, and this one is directly in my group. We have been gradually, probably slower than some people would like, trying to do that. We experienced an issue with our original data provider for that function terminating most access to that data. We've switched over so that now one benefit of the switchover is in-product financial data is using the same sources as Wolfram Alpha uses for answers on the web. In the process of doing that switchover, there were some properties that were lost, especially things related to difference between raw and adjusted, open, high, low, close values, and some other properties. Most of those things, many have been restored. There are others that are in the process of being restored right now. I think if there are particular things that aren't working the way you expect them to, they will come back. I know recently there was an issue also with volume for many equities and indices that should be fixed now as of this week with the latest deployment. It's something that we're watching closely. It's frustrating that when we rely on external data sources and we have challenges with those data sources, we try to respond as quickly as we can, but sometimes retooling things to work with a different provider can take longer than we hope. Does Wolfram Alpha rely on curated data sets to produce outputs? Is there risk of retrieving non-curated data and possibly this is somebody asking about essentially this is about the quality of data in Wolfram Alpha. Most of the data in Wolfram Alpha has gone through some curation process. The level of scrutiny that any data receives can depend on the domain and can depend on just how good the source data is. For domains like chemistry, elements, astronomical data, any of the scientific domains, certainly we're trying to rely on the most reliable, accepted, authoritative sources of data that we possibly can. In domains like people, or when we're getting birth dates and birthplaces and other sorts of things, we try to find some consensus or a best possible value in cases, but sometimes there are discrepancies between data sources and no single authoritative source. So we have to make some judgment calls. There may be certain sources we trust more than others that we will defer to and use their answer, but we are also constantly looking at improving data, double checking data, verifying data points against newer and better data sets when they become available, and trying to make the data as good as we can. Another question about cryptocurrencies. Historical prices for cryptocurrencies and financial data. This is a really good question. Actually, this is something we're actively working on right now. One of the things that has been a long-standing deficit, I think, is not having access to historical currency conversions of any type in the language, at least not in a really easily accessible way. We're actively working on this right now. I would expect to see some improvements in currency convert and inflation adjust in the near future that will cover standard currencies as well as cryptocurrencies.
I think I'm going to pass this share over to Cassidy, and we have another poll question we want to put out to you now as we transition to Aaron. This question is about data scraping, and this is a topic that Aaron will be demonstrating and talking more about in his talk. So as this poll question shows up on your screen, if you would go ahead and respond and give us a little bit of feedback, this will help guide Aaron in his presentation as he comes up next here.
All right, hi, I'm Aaron Enright, data scientist for Wolfram Alpha. And fortunately, the most popular data formats that you seem interested in scraping come to you relatively well structured. JSON is a very well structured and easily imported data format. It comes into Mathematica either as a list of rules or as an association, depending on how you import it. Spreadsheets, being tabular data, are also come in nicely as lists of lists of data. What I'm going to be focusing on today are really the top two, which tend to be treated the same way by me when I'm scraping HTML and XML. HTML especially tends to be a lot messier and a lot more difficult to deal with, but I think the Wolfram language has some great tools for dealing with them. So without further ado, let's dive into scraping some HTML. We're going to go from a website, scraping the data out of it, and doing making a data repository object out of the data that we get from that website. The website I chose today is from the U.S. presidency, the American presidency project's job approval ratings. And let's have a quick look at that. If we scroll down a little bit, we see a nice table with a bunch of numbers and dates and the president's name and so on. We've got a form up at the top where we can select a president going back to FDR up to modern times. So how to get that data out? There's a easy route to take first, which is using the import function, which we'll use a lot here today. You feed it the URL as well as the parameter data, and that imports tables from and other structured data that it can find in the website. And unfortunately, in this case, the output is not really optimal. It's kind of tough to get down to where you need, to the data that you need. We can, after examining it, you can find the data that you want, but it's really ragged and messy and tough to deal with here. Another option is using full data. What full data does is a kind of a more thorough automatic scrape of the tables in the HTML. It accounts for empty cells and cell spans and things like that. Once again, the data comes out pretty unwieldy, say the least, and the data is ragged. We still have rows of unequal lengths, and it's tough to deal with and manipulate. Being a little bit of a control freak with how I process the data, I don't like to use data and full data in my imports unless I'm able to get the data out very quickly and with minimal screwing around. Instead, what I like to use is importing a data as an XML object. The data that comes out when you import a website as an XML object looks like so. We have the head of XML object document, followed by a list, followed by a bunch of XML elements. And this gives you a symbolic representation of the HTML in the web page. If you're familiar with S expressions in Scheme or Racket, as they call it these days, it's very much like that, where you have the head XML element, the name of the element, a list containing the attributes for that element, and then another list containing the contents of that element. If we dig through here, we start finding table rows. We discover pretty quickly that the website we're dealing with, they do all their layout through tables, which if you've studied web design is kind of gets a bit of a it's a bit of a no-no, and that's why using data and full data is so unwieldy. So if we examine the source code through a web browser, it's just a screenshot of using the inspector in a web browser to examine the source code here. We notice that our table rows that we want are all of the class list date. Rather, the cells, the table data themselves in the rows have the class list date. We can use cases to extract those rows and cells pretty easily. And this is how we do that there. We've got our XML representation of data, and give cases this pattern of a table row followed by anything, followed by a list of table datas with the class list date, followed by anything, and repeated. And we give it a depth level of infinity, and that starts giving us data that looks good here. There's a row for us. We have the president's name, start date, end date of the poll, the colored cell that we see in the web page, as well as the approval, disapproval, and unsure, no data elements there. We can map over those rows there and extract just the data elements themselves. There they are. And if we check the dimensions of that, now we notice that we have some nice non-ragged data. We still need to clean up and structure the data some more now. We need to get our data is not close to ready to be put into a data set or an entity store or anything like that yet. We still need to do things like turn names into entities, turn dates into data objects, turn these numbers into quantities, and so on. So if you'll notice that in the web page, the president's name only appears on the first row. We see that up here too. There's the first row and the second row, no president's name, just an empty space, and so on. So we'll have to account for that, and we'll have to account for things that we don't want, such as the colors cells here. So at this point, I like to get my get an end structure in mind, get an idea of what I'm working towards. Ultimately, I'll want a list of associations where I have the president going to an entity object, a time series of their approval ratings, a time series of their disapproval ratings, and a time series of when they're unsure or no data. And one of these associations for each president. So here's our first step towards working towards that structure. We will take the first element of the, I'll start over on this side. We'll take the row zeta, take the rest of it on the right-hand side, and for the first part, we'll run it through the interpreter for person. And here we have Franklin Roosevelt going to a date. That's the colored swatch in the table, and then the numbers. Here you can see that we are on our way. We don't want the image element, so we will just drop that. It's in position 3 of every row. So do that, and now we're a step closer. And here we are going to combine a couple of steps. We're going to apply date object to the start date of the poll, date object to the end date of the poll. We're going to turn, if I go into here, we can see that these numbers are strings. I could use the technique that Alan used of using interpreter here. I'm using an alternate technique of using toExpression on the string to turn it into an integer, and then wrapping that in quantity and percent. And a final little cleanup step here of taking any place where we have a string, a single string within a list, and just returning that string. So we run that, we get some pretty nice looking output. You'll notice that we have these date object warnings that the dates are ambiguous. Basically, the Wolfram language is telling us it doesn't know if that's the month or if that's the month. It could be month, day, year, or day, month, year. We can get around that by providing a date specification where we give the string that we're interpreting as a date along with the order of elements in that string. So now the same thing, but without the ambiguity errors. Now we have to, now our next step is to make time series out of all of the approval, disapproval, and unsure numbers. We kind of have a decision to make here in that time series needs a single date. I don't believe at this point yet we can do a time span on the dates in the time series. So I'm kind of arbitrarily picking the end date for each poll as the date point for each time series. And so we will continue building here where we've got our data. I'm sorry, we've got our president, and then our data is what we did in the previous step. And down here, we have the data structure that we had in mind at the beginning, our final design, where we have the president, and then we take all of the data in with the approved key and put that into a time series, and same with disapproved, and same with the unsure no data. And we get that nice little output. And we're starting to have data that we can easily make a dateless plot of. And so things are looking good so far. Now we need to do this not just for FDR, but for several web pages. So we're going to package up all the steps that we made here into a single scraping function. It's basically ends up being a bit of a copy paste job of the steps that we did in the past, earlier on in the presentation, where we take our scraper, give it a URL parameter, import that URL, and within a module, set some variables in here where we'll have the rows, the data from those rows, and then the results that we're going to return. So we define that function, and we'll run that over a different one of the presidents. Picked Nixon here for this, and it looks like it worked. So now we got our function, and now we need to map it over all of the different presidents. If we examine the URL from the presidency project, you notice that it has, after the question mark, there's a bunch of different parameters, and the only parameter that changes from page to page is this president, the pres parameter, which is the number of president that we're talking about. It starts with FDR number 32 and ends with Trump number 45. So we can pretty easily just do a range of 32 to 45 and map a string join over that range, which gives us a list of URLs. And then to get our data on all the presidents, we can just map the scraper that we have over that list of URLs, which takes a moment as it's hitting several web pages. And there we go, it's done. So now we have to do various checks on our data. And one of the things that Alan mentioned was that interpreter, unless you tell it specifically that you want it to return, you can pass to interpreter an ambiguity function. We did not do that. We just said, give us your best interpretation of the input. We'll want to check what we have here with the interpretation of the presidents, and you'll notice that George W. Bush appears twice. Every other president appears only once. If we go back to the web page, when we go to, well, the list of presidents, we'll notice the first President Bush is listed as George Bush, and then the second President Bush is listed as George W. Bush. If we go to the George Bush page, we'll see what we scraped out of there was just George Bush, which interpreter, most likely because George W. Bush, being the most recent President Bush, picks him by default. We can tweak just a little bit our presidential approval scraper function to replace the plain George Bush with George H.W. Bush to fix things there so that we have the right president. And we'll give that a minute to run. In here we see now we have one instance of every president, including George H.W. Bush and George W. Bush. Now let's take our data and turn it into a data set. There we go. And I'm going to put that into the Wolfram cloud for safekeeping as well as for retrieval later on when we make a resource object out of this data. We'll make a few visualizations of the data just to explore it a little bit. Our first visualization is we will look at, we'll grab all of the approval ratings for the presidents with a, plotted as a time series. And we'll see that there. Each president has a different color with some repeating colors there. And an interesting little plot of how things have gone as far as approvals. This plot I found a little interesting, the plot of the unsure or no data points in the various presidencies, where I just found it a little fun that there's a huge peak at the beginning of every presidency, it seems, where people are actually taking their time. At least some number of people are taking their time to judge the president, which is, I think, reassuring. And used from the Wolfram knowledge base, because we have the person entities as the president, we're able to grab their images and use them in the legend for the plot to make things a little more, just a little more fun. How about aggregating the data and putting it all together? So I made a path through by joining the paths through all of the disapproval time series and making a single time series out of that. And then also a moving average with a window of 4 years or one presidential term. Just to see how the disapproval of the presidency moves over time, and the smoothed out version of it kind of gives a bit of a, I think, a bit of a better, more readable plot, but we also have it overlaid on the very detailed date list plot. So now we have our data set made, and we've put it into the cloud, and let's say we want to share it with others. So one thing that you can do is in Mathematica, you can open, a new data resource notebook. I already have one filled out. If you open a new data resource notebook, you get this blank notebook with fields to fill in and so on. I've already gone and filled one in here for us. You give it a name and title, Presidential Job Approval Ratings, a description, some more details. This data comes from the Gallup poll. It's compiled by Gerhard Peters. I'm the one contributing it to here. It'd probably be good to mention Gallup. A source reference citation, a URL source for the data, and other metadata is available here too. Categories, I chose politics. You can choose multiple categories, such as statistics and so on. And the content type, this is all time series data, and a few keywords. Here's where putting the data in the cloud is handy. You're able to, for the content element initialization section, cloud get that object that we just put up there. And there is our familiar data set. And we fill in, this code comes, this is a template that is in the data resource definition notebook when you open a new one. We're using a data set, data type, and once again, our cloud object, our default content element is that data set, and so on. So we'll evaluate those items there. And then we take the examples that we had just made. There are two default examples, retrieving the resource and retrieving the default content. And then I added here the examples that we made back in this notebook, where we have the approval of each individual president's job performance, how many people were unsure or had no data, along with photos of the presidents. And then I packaged up in a module this 3-step process here to make this smooth timeline of job disapprovals. And there we go. Now the big step to create the resource object, run this cell, which takes the evaluation notebook, packages it up into a resource object. That is done, and now we're ready to deploy it. You can deploy it locally on your computer and use it yourself. You can deploy it privately to your own cloud account, deploy it publicly to your own cloud account, which is what I'm going to do here. We'll give it a title there and cloud deploy it. Which will take a moment to, and then we click on that link and everything should have, now we have our own, you'll notice this is not in the public data repository, but rather in my own user space on the Wolfram cloud. And we'll see, here's the metadata, some of the metadata we have filled in, as well as the examples. Scroll down. This code is copyable. So if someone wants to use your resource object, they can easily just click the clipboard there, copy it to their clipboard, put it into a Mathematica window and notebook and evaluate it. And there we are. And then the source metadata that we had filled in is down at the bottom of the page. To submit it to the Wolfram data repository, you could request a publisher ID and add some information about your data resource, and then resource submit. The submission process is just up as simple as evaluating that line. So there you have, in a nutshell, a pretty simple example of going from data trapped inside HTML and making it more computable. I am ready to field questions if we have any here. Let me see.
I think we do have a few flagged for you.
I'm looking. Here we have one from Percy. Can you create a job that gets data from a web page daily, even if the data is not displayed in table format automatically? The web page needs to select options on a form, hit download, and get a table in CSV format downloaded. The short answer is yes. The long answer is that it really varies on the web page. This is something that I've dealt with, and it's kind of, it depends on the web page and how the writers of that web page, the authors of that web page, have structured their page and structured their forms. You may want to look at URL submit and URL execute functions. Depends on if they use get or post for their form data being submitted, and so on. But it's absolutely doable. If you wanted it to be something that was run daily, automatically, making your scraper a Wolfram language script and running it from a cron job or whatever job scheduler is available in your operating system is a pretty good option. I do have several reports and things that I run at work on a daily or weekly basis that are just Wolfram language scripts triggered by cron, and they go and either scrape something or run a bunch of tests and then spew output into a cloud object that then gets read by Alan or others in our organization. Can users develop their personal or enterprise data repository separate from the Wolfram data repository? Yes, and Alan could probably help me out here a little bit. You can deploy first, you can deploy something and have its permissions set to private. You can also create your own permissions group where you give a list of Wolfram Cloud accounts that are able to access.
Right. I mean, the only thing that you really don't get here is there's no way to, without you manually constructing it, to have some sort of landing page for your own personal data repository, which contains multiple data resources, and your own personal resources are not going to be searchable to other users using resource search inside the language. But as long as you have the permission set, you can certainly deploy your own resource objects to your heart's content, and share or publish links to those whatever way works for you. Those are going to be accessible to anybody else, assuming you have the permission set correctly.
Okay. Let's see, is there a way to asynchronously as opposed to serially import and process web pages? There you go. The cryptically named URL fetch asynchronous function is what you are looking for there, Dave. You can look in the documentation for that. And oh, you can see it's been superseded by URL submit, but it's still in the system and will work for you. URL submit will do the asynchronous fetching for you. There are also, it might be a good time to point out, there are also, I did a series of Twitch screencasts where I did basically, especially in the first, I did a series of 3 Twitch screencasts. In the first one, I built 2 resource objects, and the scraping notebooks and the resource object submission notebooks are available through the Wolfram Research GitHub account. So those notebooks are filled out in a little bit better detail than what I did just here. So we did like state lotteries, and there's the resource subscription. Let's just go to the top level. And this also has links to the screencasts themselves if you can't get enough of hearing me talk about scraping. There you are. Will the data science platform take care of a lot of this data wrangling, or data preparation will remain a manual task? Well, to some extent, I am of the view that a lot of the data wrangling should be automated as much as you can. It can be very tedious to do it manually, but there's always going to be some manual component to it. I try to automate things as much as possible. A huge chunk of my job is, Alan had mentioned our data curation team earlier on, and how they have to, in particular with not so much the hard sciences, but our softer areas like people and so on, where they have to inspect the data and verify facts and stuff. And I do as much a huge chunk of my job is automating as much of that data collection and verification as possible, but there still has to be a point where people have to look at, where we have to have human eyes on the data and the data sources to look at them. So we're not at that point yet where it can be fully automated, and there are some areas where, especially if you trust your data source that you're scraping and they're pretty authoritative, you can automate a lot of it, but you're not, we're not where it's just going to be push a button and thoroughly clean data comes out the other side. Yes. And the last question I see here is the Twitch URL posting would be great. As you can see, those are linked from the the GitHub page. Let's see, yeah, there we go. Becoming a Data Curator Part 2. We'll back out of that before it starts auto playing. So, okay, any other questions or anything I would be glad to answer, or?
Thanks, Aaron. I think we have covered everybody's questions. I think there's a couple people we promised to follow up with after the session, and that's fine. We will do so. You'll be getting an email from one of us here at Wolfram if you had a question we couldn't address right now on the fly. But that does conclude our presentations today and the data science webinar series. Thank you to Alan and Aaron for presenting today. We appreciate your participation, and I hope that everyone enjoyed the talks and learned about concepts and tools you can use to unleash the power of your data. We will send an email to everyone in the audience with a link to the recording of this session, and which will also have download links if you missed those earlier, didn't get a chance to download the notebooks.